Alright, this video is a part 2 of a three-part series on the method of variation of parameters. In the first video, we introduced the method and the formulas involved. In this video, we're going to start solving some examples. In particular, we're going to solve example A and example B, then example C we will do in part 3. All right, so in part A, we have got y double prime minus 4y is equals to 4xe to the 2x. We have listed the two formulas that we're going to use here. All right, so the associated homogeneous equation is going to have the characteristic equation r squared minus 4 equals to 0. This tells us that r is plus or minus 2, and so the complementary solution is going to be k1 e to the 2x plus k2 e to the minus 2x. So from here we have y1 equal to e to the 2x and y2 is equals to e to the minus 2x. The Wronskian is therefore going to be the determinant of e to the 2x, e to the minus 2x, and the first row and the second row got the derivatives of this. So here we're going to have minus e to the minus 2x. This works out to -4. And so now we can go to our first formula. So the function k1 is going to be the negative integral of y2 is e to the minus 2 tau. The non-homogeneous term is 4 tau e to the 2 tau, so that's the term on the right hand side of the equation, and then this is divided by the Wronskian. Cancelling accordingly, this just works out to tau d tau, because you have your 4 cancels out, this times that cancels out, and so this is just going to be equal to x squared over 2. So that's the k1 function. Then the k2 function is going to be the integral of y1, which is e to the 2 tau, then 4 tau e to the 2 tau all over -4. Cancelling accordingly this time gives us tau e to the 4 tau d tau. This can be evaluated using integration by parts. We're going to use tabular integration in particular. So if we write the polynomial and its derivatives in one line, and then the exponential and its integrals, so this is the integral of that, and then the integral of this is going to be 1 over 16. So this is tabular integration. Then we match them accordingly as shown by the arrows and the respective signs. So k2 is going to be equal to the negative of tau over 4 minus 1 on 16e to the 4 tau. Notice that the constants we take them to be equal to 0 without loss of generality in these calculations. So this is going to give us 1 over 16. So here we're going to then plug in x for every tau. So it's going to be x over 4 e to the power 4x. So the particular integral is going to be k1, which was x squared over 2, times y1, which is e to the 2x, and then k2, which we have just derived, x over 4, and then times y2, which is e to the 2x. And so if we combine the terms here, it will be x squared over 2 minus x over 4 plus 1 over 16, all times e to the 2x. Then the general solution yg is going to be yc plus yp. So yc is k1e to the 2x plus k2e to the minus 2x. Then we're going to have x squared over 2 minus x over 4 plus 1 over 16x to the 2x. Now, since these two terms have got the same exponential, we're going to combine them into one term. So we're going to have x squared over 2 minus x over 4 plus 1 over 16 plus k1 e to the 2x, and then there's going to be plus k2 e to the minus 2x. Now, these two are both constants, so we're going to combine them. So we can write this as x squared minus x over 4 plus k1 asterisk, where k1 asterisk is that constant there, so we can represent the final solution in that form. All right, so that is the first one. We are now going to go to part B. So in part B we have y double prime plus y is equal to secant x. Right, before we go this, let's just comment about the fact that the first example here can also be solved using the method of undetermined coefficients. Actually, we have solved this problem in our video method of undetermined coefficients part 3, which we're going to post the link for you to check out. So you can check that one there and actually confirm that it gives us the same solution. Part B, however, because this is secant, so the method of undetermined coefficients works only if the function on the right hand side is either a polynomial. So it works if this is a polynomial, or if it is an exponential, or a trigonometric function being sine or cosine of ax, or linear combinations of any of these. then the method of undetermined coefficients is going to work. So for part B, we've got secant, which is not one of these. So usually secant is a reciprocal of that one. So only the method of variation of parameters is going to work for this one. So the associated homogeneous equation is going to have that characteristic equation, and so the roots are plus or minus I, which is telling us that the complementary solution is going to be k1 cosine x plus k2 sine x. So from this, the coefficient of k1 is our y1, and the coefficient of k2 is our y2. These two are going to form the first row of our Wronskian, and then in the second row we're going to have their derivatives. This time the Wronskian works out to cosine squared plus sine squared, so the Wronskian is equal to 1. Then plugging into the formula for k1, so k1 is y2, which is sine tau, times f. The Wronskian this time is 1, so dividing that by 1 leaves it exactly as it is. So this is just a tangent, and then we know, because tangent is a standard integral, the integral of tangent is ln of secant, so we can write that as ln of cosine x. So that is our k1. Then k2 is the integral of y1 times f. So this time we just have the integral of d tau, so this thing is going to be x. And then the particular integral is going to be y1 times k1. y1 is cosine x, k1 is ln of cosine x, then k2 is x, and y2 is sine. So that's going to be our yp, and the general solution is then going to be equal to k1 cosine x plus k2 sine x, then plus cosine x times ln cosine x plus x times sine x. So we can express this as k1 plus ln cosine x times cosine by factorizing, and then the second term is going to be k2 plus x times sine x. All right, thank you very much for watching. So we're going to end this video here. Then in part 3 we're going to continue with example number C. Thank you. Hopefully it's been useful.